For the first of two example problems on the topic of Newtonian gravity, we are given two people, we're given their masses and the distance between them, and we're asked to find the force of gravity between these two people. Now, every object in the universe gravitates. Therefore, that is like saying this person will feel a gravitational force pulling to the right, and this person will feel a gravitational force pulling to the left. And we are asked to find the strength of this gravitational force. To do that, we will use Newton's law of gravity. F equals capital G, the mass of object 1, the mass of object 2, divided by the distance between these objects. Now, this capital G is a fundamental constant of nature. It determines the strength of the gravitational force. When I made that statement, I did not specify which objects are gravitating. Maybe I was talking about a ball being pulled down towards the center of the Earth, or maybe I was talking about a star being pulled towards a black hole. It really doesn't matter. This fundamental constant determines the strength of the gravitational force everywhere in the universe. Now, we sometimes use lowercase g, which is 9.8 meters per second squared. This is the acceleration of gravity if you are near the surface of the Earth. This is a constant, it has different units, and this constant determines the strength of gravity everywhere in the universe. So I just want to explicitly say these two quantities are fundamentally different things. So to answer this question, I could say the strength of the gravitational force will be given by capital G, Newton's constant, is 6.67 times 10 to the negative 11. The mass of the two people were given as 50 and 75 kilograms, so I could write that in, 50 times 75. And the separation between these people is 50 centimeters. Now, whenever we work in problems like this, we want to convert to meters. So 50 centimeters is 0.5 meters. I will divide that by 0.5 squared. And at this point, I have numbers plugged in for everything. I just hit enter on my calculator. And when I do that, I find the strength of the gravitational force between these people is going to be 1.0005 times 10 to the negative 6 newtons. So it is true that every object in your everyday life is pulling on you with its gravity. But the thing is, this force is so tiny as a result of this fundamental constant of gravity being so small that it's effectively negligible. For context, 1 pound of force is about 4 newtons, and this is less than 1/1,000,000th of 1 pound of force. For the next example problem on Newtonian gravity, we are told that we have a plumb line. A plumb line is just a mass hanging from a string. Now, you would expect normally that a mass on a string would just hang straight down. The Earth's gravity is going to pull that mass down, and the string will be perfectly vertical. However, if we place a plumb line close to a large object like a mountain, the mountain is made of stuff, the mountain does gravitate, and therefore the mass on the string will feel a gravitational force pulling it towards the mountain. So in this problem, we are told that we're going to approximate a mountain as a perfect sphere of radius 2 kilometers. Is this a good approximation for a mountain? Well, ish. We could do a lot worse. Although approximating a mountain as a perfect sphere does make this problem solvable. So we'll treat a mountain as a sphere of radius 2 kilometers or 2,000 meters, and the rock that makes up the mountain has a density of 2,600 kilograms per cubic meter. We're told that we're going to place this plumb line a distance of 6 kilometers away from the center of the mountain. So normally, if I were to imagine the mountain does not exist, I would expect the mass on the string to hang straight down. But because the mountain does exist, the mountain's gravity is going to pull the mass towards it by a little bit. So the string will not be perfectly vertical. The string will have an angle away from the vertical. So the mass on the string will actually be pulled towards the mountain by a little bit. And we are asked to find what is this angle that I'm going to call phi. Now, in the picture that I drew, the gravitational force of the mountain is actually going to be very, very tiny compared to the gravitational force due to the Earth pulling on the mass. But I needed to exaggerate this picture just to make it easier to draw. We could go ahead and draw the forces that are pulling on this mass. One of the forces pulling on the mass is going to be the force of gravity from the Earth. The Earth is trying to pull the mass straight down, so I could draw the force of gravity on the mass to look something like this. So this is the force of gravity from the Earth. There is also going to be a force of gravity of the mountain pulling on the mass. The mountain will just pull that mass on the string towards it. So I could draw the force of gravity from the mountain to look something like this. And in the setup, the mass is not accelerating. We have one force pulling it to the right, one force pulling it downward. Because this mass is not accelerating, there must be another force canceling these other forces. And this other force is going to be the force of tension in the string. So there will be a tension force pulling along the string that looks something like this. Now, at this point, I'm going to draw this picture out and we'll write the vectors in their components. So if I were to draw the mass on the string, here's the mass on the string, and the string will go up some way like this. I could draw the x and the y axes. Here's my x-axis, here's my y-axis. And I'm going to draw these vectors that are in this problem. So we have the force of gravity from the Earth is pulling it straight down. I call that Fe. I have the force of gravity from the mountain pulling it to the right. I call that Fm. And I have the force of tension pulling the mass up and to the left. So here's the force of tension that is canceling these two forces. Now, if I look at this picture, the string is going to be aligned with the force of tension. So I could say the angle of the string over here will also be whatever this angle is over here. And this angle phi is what we're ultimately trying to find. Now we are going to determine the magnitude or the strength of the gravitational force of the mountain pulling on the small mass. We will find the magnitude or the strength of the gravitational force of the Earth pulling on the small mass. And after we determine the strength of those two forces, we'll write out those forces as vectors with components. So to find the strength of the gravitational force with which the mountain pulls on the small mass, I would use Newton's law of gravity. So I could write the force of gravity of the mountain pulling on the small mass could be written as Newton's gravitational constant, capital G, times the mass of the small mass that's tied to the string, times the mass of the mountain itself, divided by the distance between these objects squared. And again, when you're talking about a sphere, you could pretend the sphere is a point particle at the center with the entire mass all concentrated there. Now, we do not know what this small m is. We are not given the mass of the object that's tied to the string. So hopefully when we work through this problem, that number will end up canceling out nicely. We do have the mass of the mountain itself, though. We don't have the mass directly, but we are given the density of the rock that fills up the mountain. We are given the size and shape of the mountain, and that will be enough information to determine the entire mass of the mountain itself. So density, when you're talking mass density, is related to mass and volume, as density is equal to total mass divided by total volume, as long as your mass is evenly distributed throughout your object, which we assume is the case here. So density in physics is usually specified with a lowercase Greek letter rho. It does look like a lowercase p, but I will often make rho curvy just to help avoid confusion with the lowercase p. M is the total mass of the mountain itself, and V is the volume of the mountain. We are not given the volume of the mountain directly, but we are told that you could approximate the mountain as a sphere of radius 2,000 meters. So if I go to Wikipedia or a textbook cover and look up the volume of a sphere, I would see the volume of a sphere is 4/3 pi r cubed. So I could write the mass of the mountain itself as rho times V. So that would be the density of the rock times the volume of a sphere. So that would be 4/3 pi r cubed. And here I'm using capital R because I'm talking about the radius of the sphere rather than lowercase r, because I don't want to confuse these two terms. In this problem, they mean different things. So if I plug these numbers in a calculator, I would get the mass of the mountain itself is 2,600 kilograms per cubic meter times 4/3 pi times 2,000 cube. And when I plug this through, hit enter, I get 8.7 times 10 to the 13 kilogram. So the mass of my mountain is really, really large, and we expect that. Mountains are big, they're made of rock, they're going to be very heavy. Now, as I said, I do not have the mass of the small object that is tied to the string. So even though I said we're finding the magnitude of this force of gravity, it's probably more accurate to say we're finding this force of gravity as much as we can. There will still be an unknown. We won't have a number for the magnitude of this force of gravity. So I could then write that the force of gravity from the mountain is given as 6.67 times 10 to the negative 11 times the mass of the small object that is tied to the string times the mass of the entire mountain itself, this really big number, 8.7 times 10 to the 13, divided by the distance from the mass tied to the string to the center of the mountain. Technically, if we say this is 6 kilometers, this will technically be a little bit less than 6 kilometers because the mass is shifted a little bit closer to the mountain. But this is so small compared to the 6 kilometer distance, we could just approximate 6 kilometers. So divided by 6 kilometers, that will be 3 times 2,000. That will be 6,000 meters squared. And when I send these numbers through a calculator, I find the gravitational force on the small mass from the mountain is 0.00016 times the mass of the small object that is tied to the string. So this answer is not 0.00016 meters. This is not a unit. This small m here is the mass of the small object that's tied to a string. So if it's 16 grams or 500 grams or 2 kilograms, that will change the strength of this force. But again, as I said before, we are not given what this little m is, so hopefully this little m will end up canceling out. So I could write the strength of this gravitational force from the mountain is 0.00016 times the mass of the small object tied to the string. Now, what can I say about the strength of the gravitational force of the Earth pulling down on that small mass? Well, this is going to be a lot easier. Because this small mass is relatively close to the surface of the Earth, I could write the force of the Earth pulling down on the small mass is going to be m times 9.8. 9.8 is the acceleration due to gravity when you're within a few kilometers of the surface of the Earth, and this is good enough. Now, if I really wanted to, I could have said, okay, here is the entire Earth, here's that mass that is close to the surface of the Earth, and then I could say, what is this distance? This would be the radius of the Earth, and then I could look up the mass of the Earth, go through Newton's law of gravity, but I would end up getting this exact same result. So I'm going to just do the problem this way. Now, let us write the components of these two forces in their with their x directions and their y directions specified. So I could say the force of gravity from the mountain in the x direction will be whatever this number is, 0.00016 times the small mass, whatever that number is. The force of gravity from the mountain in the y direction will just be 0 because the mountain is entirely pulling to the right. The force of gravity from the Earth in the x direction is going to be 0. The force of gravity from the Earth in the y direction will be negative 9.8 times the small mass, whatever that number happens to be. And negative because the force of gravity is pulling downward. Let us look at this picture again. Now, I reason that if the small mass is just hanging there, if it's not accelerating or doing anything interesting, this tension force must cancel these two pulls of gravity. And if I look at this picture even closer, the tension force to the left will be canceled by the force of gravity from the mountain. And the tension force, the component of tension that pulls upward, will be canceled by the force of gravity of the Earth pulling downward. So I could think of that as this will be canceled by F tension in the x direction, and this term will be canceled by F tension in the y direction. And so if I imagine that I am adding these two vectors together, these two forces of gravity, I could say the total force of gravity is going to be something like this. So this is the total force of gravity, the force of gravity due to both the mountain and the Earth. And I know the components of this total force of gravity. The x component of this vector is going to be 0.00016 m, and the y component of this force of gravity is going to be negative 9.8 m. And if I think about this problem in this context, I notice my angle phi that I'm trying to find is also going to be right there. So this question essentially then becomes, if I have a right triangle where one side length has a magnitude 9.8 times m, and one side has a side length of 0.00016 m, what is this angle up here? And to find this angle, we could just use inverse tangent. Right now, I am talking the side lengths, so I'm not worrying about positive, negative sign. Ultimately, I only want the amount, the size of this angle. I'm not really worrying about directions with vectors anymore. So I could write that tan inverse of opposite over adjacent 0.00016 m divided by 9.8 m. And look what happened. We have an M upstairs and downstairs. Even though we don't know the mass of the object that's hanging by the string, these masses still will cancel. And so I could say my angle phi is going to be given as phi is equal to tan inverse of 0.00016 divided by 9.8. And when I put that in a calculator, I get phi is equal to a very small angle, 0.000935 degrees.